Munich, Germany in 2019. Since 2022, he has been working as a staff engineer in product definition and application engineering at Infineon Technologies, Austria, and is currently responsible for the CoolSiC MOSFET 400-volt G2 portfolio. Following today's presentation, we'll have a live Q&A with Mark and Sriram, and you could submit questions at any time during our session using that chat box that's over on the right-hand side of your screen. Thank you so much for joining us today, and with that, I'll hand it off to Mark and Sriram for the presentation.
Hello, my name is Mark Thomas.
My name is Sriram.
And we're here today to present to you our latest 400-volt silicon carbide MOSFET and show you some target applications and motivation why we have this product. So just introducing ourselves.
So I'm working as a staff engineer, product definition and application engineering at Infineon Technologies, Austria, and I'm responsible for the CoolSiC 400-volt portfolio.
And my name is Mark Thomas. I'm in the product marketing here in Infineon and responsible for the launch of the 400-volt silicon carbide MOSFET. And I'm looking forward to sharing more details about this product with you. So let me just start with giving you a brief introduction of the motivation behind this new product. So when we look at our silicon carbide MOSFET technologies, we see a lot of suppliers creating new generations of technology of silicon carbide, but what we also see is more and more voltage classes being created as well. So why are the voltage classes being created? And the main reason is to optimize the silicon carbide MOSFET performance for the applications and to get this cost optimization. So, and this is why we did the 400-volt silicon carbide MOSFET, and we explain more details exactly what we would like to achieve with this product. Just looking at the overall portfolio of the silicon carbide MOSFET here at Infineon, and as you say, there is an ever-increasing number of voltage classes, and in here the 400-volt is the lowest blocking voltage silicon carbide MOSFET we have in our portfolio, and what we see on the market today. So it's really a breakthrough product. And we see really strong advantages of this product. And again, this is what we shared today. Why did we do the 400-volt in more details? So we see that we have 200-volt or 250-volt silicon carbide MOSFETs available on the market. When we want to extend the blocking voltage to higher voltages, we see these
250-volt silicon MOSFETs.
Silicon MOSFETs. Thank you very much for the correction. That's they're up to 250-volt silicon MOSFETs, blocking voltage. And when we wanted to extend this blocking voltage to higher voltages, the efficiency or the effectiveness of these MOSFETs we were not seeing. Likewise, when we were reducing the blocking voltage down from 650 volts down to lower voltages, again, we were seeing this situation. And in the end of the day, the 400-volt was a little bit of a no man's land. But we see that there were really applications and real value propositions that could be addressed with 400-volt. And we saw here now with our Gen2 MOSFET technology that we could address 400-volt very, very effectively to offer this efficiency and cost position. The efficiency is coming with these ultra-low switching losses and on-state resistance of the technology. And again, this is what we will go into more detail. The portfolio that we have, this is the first wave portfolio, SMD mounted packages, so the TO leadless package and the D square package, and we're ranging from 11 milliohms up to 45 milliohms. So let's go into some more interesting details, and here with Sriram, this is the opportunity to go into some details and share some really cool aspects of the product. So let's start with the simple question: what are the key features and benefits of the product?
Thank you, Mark. So looking one level deeper, I'd like to go into the reason why we did the CoolSiC 400-volt Gen 2 portfolio. And we see this as an enabler for innovative topologies. And here we're targeting 3-level flying cap PFCs, 3-level ANPC-like topologies, multi-level topologies in essence, but also simplifying existing solutions where there is basically no need to have a higher blocking voltage, and you have a need to block 200 to 300 volts in a simple 2-level topology. So here is why we made the 400 volt SiC and positioned it to cover a gap between the 200, 250 volt silicon switches and the 600, 650 silicon carbide, GaN, and other silicon CoolMOS like technologies. Looking at what benefit it brings at system level to optimize performance and cost, you have an R1A reduction, which helps in minimizing the system level costs. You have also the figures of merit improvement. By this, what we mean is basically the QGD, QoSs, QFR, and EOSs. And these switching figures of merit help you in optimizing the switching losses. In addition, also the rds-on versus temperature characteristics are quite flat, with a minimal increase at 100 degrees Celsius. That's about 11%. And this helps you in also optimizing your conduction losses at system level. How does it switch? Well, thanks to the super good forms and linear COSs, there is a possibility to switch very fast, but also quite controllable. So the slew rates are very much controllable and depending on the system needs. So there are applications which need to switch at a low speed, 5 volts per nanosecond, 10 volts per nanosecond, and so on. And there are applications which need to switch as fast as possible to get that highest performance. So we are catering to all of these needs to cover a broad range of applications. And thanks to the low QFR, the ringing and the overshoots, these are also minimized, leading to a better EMI performance. How do we use it? Basically, we recommend for CoolSiC Gen2 unipolar gate driving. That means 0 volts turn off, 18 volts turn on voltages, and this is enabled by a high threshold voltage of 4.5 volts. And this also helps to mitigate any parasitic turn on that could occur, and especially in non-optimized layouts. So moving forward, to delve a little bit deeper into the switching figures of merit and how they compare with reference technologies, the 650 volt CoolSiC Gen2 and 750 volt CoolSiC Gen1, which are the released reference parts in this slide that you see referenced. On the left hand side, you see the figures of merit, the switching figures of merit, and you see a significant improvement in EOSs, QoSs, and QFR. These are typically what block or limit your switching performance, and these have been significantly reduced. And this also gives you a glimpse into what could happen if you move from a 2-level to a 3-level solution, especially looking at the form EOSs, because all of these forms have been defined at the right voltage levels for each of these switch voltage class technologies. And on the right hand side, you see the conduction losses, and especially at 100 degrees Celsius, which is what typical FR4 designs, PCB designs are limited to, you see a barely about 11% increase at 100 degrees Celsius. Yeah, this is helping you in achieving the highest possible efficiency and power density, especially in multi-level topologies.
So this is really the key feature of the technology. So as Sriram was saying, the switching and the conduction losses are really significantly improved with the different voltage class. So moving to the 400 volt is really a clear advantage of using this lower blocking voltage. And this is then saying, well, where do we use this technology? Where do we use 400 volts? And this is what we will lead to in this presentation.
Exactly. And we were talking about the switching form and the QFR. And in this body diode characterization double pulse test, what you see on the left hand side is basically the drain source voltage as well as the drain source current. So in this, the first part, you see the body diode is conducting with a negative current of about 20 amps. And as the hard switching MOSFET turns on, the current decays naturally to 0, and then you have what typically is known as the QRR. But in the world of silicon carbide MOSFETs, we are giving it a new nomenclature. We're calling this QFR. What we mean by this is the forward directory of the MOSFET. And the reason why we're calling it this is because the bipolar contribution to the QRR, the real QRR, is quite minimal. And a large part of what we measure here is basically the QoSS is also included. And therefore, the QFR is QoSS plus Q bipolar. And because a large part of it is QoSS, it is lossless. And in this case, you also see the temperature and load current dependence on the switching waveforms at 25 degrees Celsius and 150 degrees Celsius on the left. There is barely any difference between the two overlapping waveforms. And on the right hand side, you see the impact of the load current from 11 amperes to about 37.1 amps for the 11 milliohm 400 volt silicon carbide MOSFET. And you see that again on the right hand side, the dependence of the ringing of the overshoots is quite minimal, depending on temperature or load current, which also points to the fact that you have a low bipolar contribution to the QFR. Next slide, please. Going into the gate drive possibilities. So we have released this CoolSiC 400 volt Gen2 portfolio in TO leadless and D2 pack 7-pin packages. And I'd like to focus on the TO leadless package because it offers a very low internal source inductance of about half a nanohenry. And this enables driving by using it as a 4-pin device using the Kelvin source, as you see on the left hand side, or using it as a 3-pin device and leveraging the benefits offered by the common source inductance in slowing down the switching or even avoiding parasitic turn on in the soft switching MOSFET of a half bridge, essentially. So one other point to reiterate here is that we recommend unipolar gate driving, 0 to 18 volts. And thanks to the low figures of merit, it is possible to switch fast, enabling higher switching frequencies, reduce dead times, and effectively higher power density because higher switching frequencies enable the reduction in the size of passives, inductors, and capacitors in any given topology. How does the switching waveforms look? Here showing you the switching performance in a 2-level buck with a switching frequency of about 65 kilohertz, a 50% duty cycle, switching 200 volts with output typically around 100 volts. And I'd like to show you the impact of the gate drive network on the slew rates. And this is to elaborate on the fact that the silicon carbide MOSFETs from Infineon are highly controllable and switch clean. Here you see switching DVDTs of anywhere from 40 to 65 volts per nanosecond. And like I said, we have the possibility to use Kelvin source gate driving, 4-pin gate driving with, in this case, you see with 1 ohm, you have the possibility to switch as fast as possible, 65 volts per nanosecond. And if the application needs slowing down, it is possible to increase the external gate resistance to about 3 ohms and reduce it to 40 volts per nanosecond. It is also possible to keep the external gate resistance as 1 ohm and just use the power source as reference and use it as a 3-pin device and still get to about 40 volts per nanosecond. And all of this at little to no penalty in efficiency. So on the right hand side, what you see are the efficiency curves plotted for different load currents. And you see here that the gate drive network has only minimal impact on the efficiency. And thanks to the linear COSs, the overshoots, no matter how fast you switch, are about 320 volts, nowhere higher. That enables also sufficient derating, for example, 80% derating, which is mandated in certain applications by different standards. Another point to keep in mind here is the system level improvements will be reflected by these clean switching waveforms, potentially also resulting in good EMI performance, reduced EMI filter sizes, and so on. I'd like to also show you how the switching waveforms look with the highest RDA zone part, the 45 milliohm part, which has super low capacitances and charges, which help to switch as high as 100 volts per nanosecond and beyond even. With in this case, you see 1 ohm and 5 ohms of external gate resistance using Kelvin source or using power source, 1 ohm gate resistance. The switching speeds are quite fast. And on the right hand side, you see the efficiency figures again showing minimal impact on the efficiency, how fast you switch, how controllable you can choose to switch. And the peak efficiency, if I may point out here, is reaching upwards of 99.1, close to even 99.2%. And these two-level measurements get translatable to the performance that you can expect in a multi-level topology. For example, the three-level flying cap PFC application, which we are also positioning for AI servers, which need the highest efficiency numbers for energy savings and lower emissions.
Yeah, so thanks very much for that, Shriram. So those waveforms look very, very impressive, I have to say. So these are measured waveforms; they're not simulated. So they look really very, very clean. So this is
and all of them with unipolar gate driving, 18 volts and 0 volts turn off.
So it is really an impressive technology, and now we talk about where can we use this new 400 volt silicon carbide MOSFET. So you mentioned 2-level and 3-level topology. So what is a 2-level and 3-level topology?
There was an interesting publication from Yole,
yes,
and you see this on the slide also referenced. A 2-level topology is a simple half bridge. So there is a bus and you have 2 switches, and the output of this half bridge swings between the high side, which is typically VDC, and 0. And on the right hand side, you see multi-level topologies, in this case 3-level topologies. On the left hand side, the neutral point clamped, and on the right hand side, the flying capacitor. So here you have, instead of just 2 levels, multiple levels. We'll see this in another subsequent coming slide. You also see here various advantages and disadvantages of these approaches. And the greatest thing about Infineon is we have different voltage classes of the CoolSiC technology, but also other technologies, which provide the designers to go in various directions. We are addressing the whole trends, the different trends that the market is seeing, the industry is researching and walking towards.
And so this is one of the key messages as well from this Yole report is this multi-level topologies is not university confined anymore. This is really being found in the industry, in the market. So, and now with these different voltage classes, it's the designers who are deciding 2-level, 3-level, depending on their requirements and their BOM cost budgets. So let's go in a little bit more detail. So we look briefly at the 2-level, 3-level, but how is there a guidance? What would you say what would make it simple to know where to use the device?
So it is imperative to know what voltages we are talking about in a system, right? So a typical DC link voltage, it could be an AC supply voltage. So let's look at the first scenario where we have a DC link voltage less than or equal to 300 volts, could be 150 to 300 volts. We see that it is a perfect fit for the 400 volt silicon carbide technology, where today a designer has no choice but to use either a 600 or 650 volt device, or redesign the system and go for a higher DC link voltage to leverage the full benefits offered by the higher voltage switches. So these are limits that the 400 volt SiC is looking to solve, right? This is, let me go one level detailed. So I'd like to give you a couple of examples here, looking at a case study here where you see an industrial power supply on the left and right, which has an input voltage on the left hand side of 100 to 120 volts input. And these are grids typically seen in the US, in Japan, for example, also, where you need a PFC because of the power levels. But today, there is no good switch to use in a 2-level CCM totem pole, for example.
So an optimized switch.
An optimized switch, exactly. And so the 400 volt SiC enables these kind of systems where you have the possibility to design with a lower bus voltage. And why would you want to do this? Because you have excellent hard switching forms because of the optimization of a 400 volt device. You also have a better price and performance compared to higher voltage switches. This is the reason why you would be motivated in using a lower voltage silicon carbide MOSFET. Another side is basically, on the right hand side, I'm showing you a system where you have a higher output voltage, DC voltage. This could be now a secondary side of a phase shift full bridge of an LLC with center tap rectification, where your blocking voltages are quite close to 300 volts again. And in this kind of an application, it's typically a soft switching, zero voltage switched, perhaps non-zero current switched applications where your RDA zone dependence on the temperature is important. The package is also quite important. The TO leadless and D squared packages help in dissipating heat, and also the lower bipolar contribution of the body diode to the QRR or QFR is also quite important in minimizing the ringing, overshoots, and so on, the EMI spectrum.
So it's really the bus voltage is the key decider. So there's no differentiation whether it's a primary or secondary side or soft or hard switching. It's really the bus voltage.
Absolutely. So for different hard switching and soft switching applications, the CoolSiC 400 MOSFET is a perfect fit and has been optimized to be so. The second scenario is for higher bus voltages, higher than 300 volts, could be 400 to 650 even, where you need performance and their multi-level topologies. Using the 400 volt SiC can give you the lowest switching losses, and potentially in some topologies like the 3-level flying cap, totem pole PFC, the effective inherent switching frequency doubling to result in twice the ripple frequency inductor seen by the inductor also helps in reducing the size of the inductor and effectively then also improving the power density. So here a 3-level topology with a typical bus voltage of 400 to 600 volt, this is what we see to be a good fit, and I'd like to show this how this 3-level topology looks like. And we were talking about the waveforms. On the left hand side you see a 2-level HERIC, for example a solar application where the switching node voltage goes from 0 to plus or minus DC link voltages. And with a multi-level topology like you see on the right hand side, A and PC, you have the possibility to have multiple levels between the 0 and DC link voltage. So this improves the quality of the switching node voltage waveform, helping in reducing the volt second seen by the filter inductor, and also it results in a reduced DVDT for a better EMI performance. So this is rounding up what we were talking about in the advantages of multi-level topologies using 400 volt SiC. I have one other slide which shows how the 400 volt SiC can fit in exactly the same or similar topology depending on the input voltage and output voltages. So on the left hand side, like I was saying, for grids which are less than 180 volts, 120 volt systems like in the US and Japan, could also be online UPS systems for these grids, or MPPT DC-DC converters, buck boost converters, and energy storage systems which all have a DC link voltage less than or equal to 300 volts. These switches are a very good fit, and in applications like AI servers or data centers where you have an AC line typically 180 volts to up to 350 volts is also in discussion now, or for grid systems in Canada, for example, where you have also this 347 volts line to neutral voltages. Using a multi-level topology can help you in reaching that extra bit of performance. And we have a very good deep dive for this particular application. It's there on the web pages of the CoolSiC 400 volt MOSFETs. You're free to have a look at this also to get a little bit deeper into what we have to offer.
Okay, so that was a very thorough deep dive into the different topologies and the 2-level and 3-level. But is there a simpler, easier, let's say, way to remember this?
Yes. So think about the DC link. So anywhere around 600 to 650 volts, DC link would be, targetable with a 3-level topology. And if the DC link is half of that, about 300, 350, then you can still use a simple 2-level topology. Could be an interleaved buck boost, could be a 2-level totem pole PFC, a B6 motor drive application. There are a multitude of topologies that can be addressed with a 400 volt MOSFET.
So a multitude of topologies, but a multitude of applications as well. So this is also important to note that this is it's really a universal device. So when we were creating the let's say the outlook of the market, we were really identifying a multitude of applications that this could address. And this, I think, when we look at the breakdown, we can see whether it's an AC line voltage or a battery operated voltage, then there are many applications to be selected. So this is what we wanted to show here is just a simple overview. Again, there's 300 volt, 600 volt, or 2-level, 3-level. And to give a very simple overview, and hopefully this is something we can take away after the meeting. The message gets taken away.
And a quick overview of the different topologies we are talking about to address with the 400 volt silicon carbide. The 3-level CCM flying cap totem pole PFC has been a high runner, has been seeing also quite a bit of interest in the industry recently, thanks to the release of the 400 volt silicon carbide. Also, the 2-level topologies for solar applications and energy storage has been now ramping up slowly. And synchronous rectification and solid state switches, this is also something which we're looking to explore with this new 400 volt silicon carbide MOSFET. So, Mark, do you want to give some insights into a design example?
Yeah, I mean, you are the expert here. So, I mean, this is again this 2-level, 3-level, let's say, a selection point, isn't it? So there's always a trade-off. So, and the customer has commercial budgets and also operating budgets. So in terms of efficiency and power density, and this is what we wanted to show here. This transition from a 2-level to a 3-level, say 3-level flying cap totem pole PFC. Some design, let's say, options that they have. So with this switching frequency, and so with the same switching frequency and different switching frequencies.
Exactly. So it comes down to the topology benefit in a 3-level flying cap topology. So if you look at the device level switching frequency, it could be 32.5 kilohertz or 65 kilohertz in the 3-level topology that you see on the right here. And depending on whatever you choose, the frequency seen by the inductor is double. And when you couple this with the fact that the voltage swing seen by the choke are also half, this results in a potential reduction in the size of the inductor by a factor of 1/4, so 25% smaller. And on top of my head, I've seen PFCs where 500 microhenry chokes have been used in a 2-level solution that you see on the left. And that could easily be reduced by a factor of 4. And this is what we're looking to do also in our eval boards and reference designs that we're now working on.
And this is a really important point, actually, because when people see the number of switches has actually increased, you automatically think it's going to be a bigger design.
Yeah. That is not necessarily the case, because to achieve the same level of performance, you can still come close with a 2-level design, but with interleaving, which means you still need twice the switches. What we're doing with the 3-level topology is, if I have to call it, it's series interleaving. So that is what results in twice the ripple frequency at the inductor level. And yeah, that has its own benefits, because you're also, the voltage swings across the VDS of the switches are also halved, which means your switching losses are significantly reduced when you also use a switching form optimized device for a low voltage blocking.
So the system size saving comes from the smaller inductor and the EMI filter.
And you get a higher performance.
Yeah.
Yeah.
So what we saw coming from customer feedback is when they were trying a 2-level topology using 650 volt devices and moving to a 3-level with the 400 volt devices, they were seeing an increase in the power density. So even with an increase in the number of switches, they saw a higher power density and they saw higher efficiency. So there's really a clear value proposition here, but the customer has to value this. So there is additional complexity moving to 2 levels or moving to 3 levels, sorry. So this can't be ignored, but the customer needs to have that need for this value. Mm-hmm. Otherwise, we still recommend the 650 volt switches if the 2 level is enough. But we're driving for higher efficiency and higher power density. That's our goal here with the multi-level topologies. Mm-hmm. So now we were talking about different applications and different levels of 2 level, 3 levels. Mm-hmm. So what demo boards are available to help here?
And these are important, Mark, also because of these challenges in multi-level topologies. And therefore, let me first focus on the simpler versions, basically the eval board, which uses B6 with a higher DC link voltage for batteries, which can go up to 288 volts for motor drive applications where you have a higher bus voltage or battery voltage. This is coming soon also towards the end of this year. There is also the 3-level ANPC eval board, which is targeting even higher bus voltages. And now this can target LEVs, drive applications, motor control applications, or energy storage and solar applications, which have a higher bus voltage. And yeah, we also have a 3-level buck eval board, which will be a little bit unique because this will be highly configurable. You can use this 3-level buck as a 2-level buck if you need to, with a higher voltage rated MOSFET like the 650 volt silicon carbide MOSFETs. You also have the possibility to play with, because it's a flying cap buck, 3-level flying cap buck, you're also getting a flavor of the multi-level topologies even here without having to worry about the AC-DC operation. It is a simple DC-DC converter. And this helps you also understand how you can do gate drive design with isolated supplies, custom planar transformer approach there. And there is also the possibility to try out unipolar driving, bipolar driving, 3-pin gate drive, 4-pin gate drive. So this should be available to order on ISAR towards the end of the year as well.
So we really would like to make these designs accessible and understandable, because I think just standing here showing PowerPoint slides is a great introduction, but getting your hands on these products and feeling confident that you can use them and they are showing good performance, I think this is the key selling feature that we can communicate the best. So we're happy with these boards, but they're not the only ones, are they?
Absolutely not. The champion boards are coming next. So the 3-level flying cap totem pole PFC, the technology demonstrator has already been used extensively internally at Infineon to benchmark the performance of the 400 volt SiC devices at system level. So the technology demonstrator in this case can go up to 2.8 kilowatt in the AC-DC operation. You see here the daughter board that has the 4 MOSFETs, the 4 silicon carbide MOSFETs of the 3-level flying cap totem pole PFC along with the choke. You can see more details on the deep dive AI presentation on the web pages. This is also getting ramped up to a 12 kilowatt version thanks to the power hungry AI server application, which is now also in the works, which also uses a novel concept for also the DC-DC LNC stage, in addition to the 3-level flying cap PFC stage. And lastly, we have also the 3 kilowatt 3-level flying cap PFC eval board, which will be released on ISAR. This is also towards the end of the year. And this hopefully will address also all concerns about the flying capacitor pre-charging, startup, balancing of the flying cap during operation, and gate drive for all the 4 floating MOSFETs.
Yeah, these are really open questions that are raised and we have solutions for. But the board is really a demonstrator to show that this is really under control and a key feature for the operation of the flying cap.
The solutions have been around for long, but it has to be packaged and taken to the customers and help them design in multi-level topologies, especially for applications which need this level of performance.
Yeah.
That's the goal of this board.
Yes. And it's ease of access. This is ease of learning and reduction of risk. So the designers feel confident again designing this product. So where can I find additional information? And Sriram, what is available?
So the web pages have, in addition to the data sheet, the simulation models, a series of presentations which go into the details of the different applications, the different system level evaluations that we have done to benchmark the performance of the CoolSiC 400 volt Gen 2 MOSFETs. Please feel free to go have a look at the web pages. Also, like I said, the AI PSU roadmap has even going up to 12 kilowatt PSUs for single phase PSU applications.
Which is really, this 12 kilowatt is benchmark.
Yeah.
There is nothing else like it. Yeah, so basically what we would like to do is thank you very much for taking part in this webinar and having interest in our 400 volt silicon carbide MOSFET. I thank Sriram for his expertise and
thank you
effort and time here. Really appreciate it. And yeah, we're open for questions coming from the live audience. Thank you.
Thank you.
Well, thank you very much, Mark and Sriram, for that presentation. Learning a lot about this MOSFET 400 volt technology certainly puts to shame some of the circuits that I've built with the much smaller MOSFET technology in the past. So this is very interesting. Lots of great insights. And I see some questions coming in. So are we ready to address a few of these Q&As?
Absolutely.
So the first question, and I believe it was addressed close to the beginning of the presentation, but could probably be reiterated just a bit, says, has the 400 volt SiC MOSFET technology been specific